learning the lesson now. So we're going to take notes today. These are examples out of your textbook. If you learn best by writing, and you can write these down, it'll help you remember, feel free to do so. If you learn best by watching, do that. Just make sure if you need them, you print out the notes later on. All right. Today we're going to do some of the application of why we bothered to learn factoring. Part of it. You're going to be using factoring as long as you're in math. So, today we're going to look at finding zeros of a function. And what does a zero of a function mean? Oh, right. It is going to be the x-intercept because that's where the value of the function is zero. Okay, so we're going to find, and first of all, let's go back and just do it the way we know how. Find the zeros of the function. All right, we're going to do it by graphing. So how would we graph this function right now? What do we do? Okay, what do you think?
You would need to change it to negative b. You would use negative b over 2a.
Excellent. You would use negative b over 2a, and we're using negative b over 2a to find the vertex, aren't we? The negative b over 2a is going to give us that axis of symmetry, which is your x value at the vertex. So in this problem, it would be negative 2 over 2 times 1. So the x value at the vertex is negative 1. Now, how would we find the y value at that vertex? Plug it in. So we're going to evaluate f of negative 1. So when we plug in negative 1, let's see what we get out. We get 2 times negative 1 minus 3. So this is 1 minus 2 minus 3 is negative 4. So we know this function has a vertex located at the point negative 1, negative 4. And I'm going to switch colors so it'll show up better on my graph. Negative 1, negative 4 in blue there. And then how would I graph a quadratic that had a leading coefficient of an understood positive 1?
Over 1 up 1.
And you'd square
Over 1.
Over 2 up 4.
Okay, good. Over 2 up 4. All right, because we're squaring. It's a squaring function. And then we get this nice little parabola. Okay, so that's what we already knew. So today we're going to add another tool to our toolbox. We already knew how to do it this way. And now we're going to take this same function and go, well, that function, this right side looks like a trinomial. Can you factor that trinomial?
Yeah, you can.
Okay, how does this trinomial factor?
Well, it's x.
No, it's not.
Well, x.
X plus 3.
X minus 1 and x plus 3. Excellent.
Yeah.
And if we were trying to find the zeros of the function, which is what it asked us to do first, what would we plug in for f of x? Zero. Okay, so now we have this product of our two factors. This factor times this factor equals 0. Well, to make a product 0, doesn't one of these factors have to equal 0? Because 0 times anything is 0. All right, so what can we plug into this first factor so that we get out 0? 1. What could we plug into this second factor? Negative 3. All right, let's look at that graph we just did. Does this graph have a 0 at 1 and negative 3?
No, it's so
Isn't that cool?
That's pretty easy. Wait, that's not the easy part.
Jake needs to
It's
go
going to get
back.
harder.
Isn't that cool?
Jake Arnold
So
wants you to
now,
go over again.
so we had all this just a second ago with our other method, and now with this method, so far we just have that. And we know it's going to end up making the same parabola because we started out with the same equation. So we already know where the vertex is because we cheated and did it a different way first. But we know a quadratic has to be symmetric. So if we have two zeros, right in the middle of those zeros is what? The vertex. And the vertex lies on the axis of symmetry. So we know that that's not straight at all. We can pretend. Woo! Wrong button. We can pretend. We can pretend it's straight, and that's better than making the whole page disappear. Okay. So we know that axis of symmetry is somewhere on that line, don't we? So we can get it because we know it's halfway in between. We know x at the vertex has to be -1 because that's halfway between 1 and 3. And 1 and negative 3. And if I found halfway, wouldn't I just add up and divide by 2? What's negative 2 divided by 2? Negative 1. Isn't that another way? Look, we used to do negative b over 2a. Isn't this another method? Okay, so the thing about finding the y, though, we still have to plug it in, and since we just did it right here, we have the exact same x value. We're not going to plug it in again. We know it has to be at negative 1, negative 4. Now, could we have done that without plugging this in? Yes. Because we look at this, and we go, okay, it's a leading coefficient of positive 1. Are there any stretches or compressions? No.
You just do the
So we just do the moves backwards.
Oh.
If this is over 2, I know I had to go up 4. So let's go backwards. Down 4, left 2, boom, vertex.
Alright, that was pretty easy.
So now, oh, I love putting all the pieces together. So now it is another way of graphing. And this is graphing in factored form.
I like this so much.
And when we graph in factored form, we still might have a coefficient. This time it was just positive 1. But we're going to have x minus one of our zeros, we could call it p, and x minus the other 0 that we could call q. So this is if we let p and q represent our zeros.
Doesn't matter which 0 they are.
No. No. Okay, so it's always helpful to see it one more time. So let's look at it one more time. And let's do this one completely by factoring. Let's not go back to what we already know, though that is a choice. If we were to graph this by factoring, putting it in factored form, so that's the first thing I want to see. Does this one factor?
Yes.
Yes. How does this function factor?
X minus 6 and x minus 2.
Okay, so I have these two factors, x minus 6 and x minus 2. So the first thing I did was I found the zeros of the function. And to find the zeros of the function, I'm obviously plugging in 0 for f of x. Okay, now this is a product of two factors, so either factor could equal 0. So if I plugged in 6, I'll get out a 0. If I plug in 2, I'll get out a 0. So I know I have a 0 at 6, and I know I have a 0 at, well, 6 and 2. Where's the vertex? What's the x value at the vertex?
4.
4. It's halfway in between. 2 plus 6 is 8, divided by 2 is 4. X equals 4 is my axis of symmetry. Was there any stretch or compression that I have to deal with? No. So I can go down 4 over 2, vertex, boom.
Oh, that's so cool.
So beautiful. So beautiful.
Why didn't we learn this first? This is so much.
I wish we had this.
This is awesome.
This
okay?
is awesome.
I'm smiling.
Okay.
I'm having so much fun.
All right, well, we have to learn how to factor before we could do this.
Well, I know. I just wish that like this was our first time.
Okay. All right. But, you know, sometimes they won't factor.
Well, that's true.
And when they don't factor, we'd have to use the other method, wouldn't we? Yeah. All right, so let's take a look at this one. This one factors differently, but it still factors. Okay, so this one just has a GCF, doesn't it?
3x.
What is it? 3x.
Yeah.
Okay, let me see if I can write the number 3. There we go. I can do it. So it factors to 3x times x plus 4. So I still have two factors. 3x is one of my factors, and then x plus 4 is my other factor. Okay. What can I plug in to make this 0? Good.
Negative 4.
0 and negative 4. So I've got one here. I've got one here.
Is that negative 2?
Negative 2 is
Negative 2 is good.
Okay, so negative 2 is the axis of symmetry.
Down 4 over 2.
No. No, because
Right.
there's a stretch.
Okay, so this one does have the stretch.
3.
This one does have the stretch. So we have to be a little more careful.
Doesn't go down.
Okay, so it has the vertical stretch by the factor of 3.
Go down 12.
So we would go down 12 over 2, so it's way down here.
Right.
We'll call this the point
Killing it.
-2, -12. And then we have our very much, totally didn't even come close to 0, but I had all best, that's horrible. That's just, there's no excuse. Okay, so, in reality, I would have loved to have hit my zeros when I was graphing it, but it just didn't happen. All right, so let's look at example 4.
Oh, great.
In example 4, do you see a divide by 3, a divide by 3, a divide by 3?
Yeah.
Do y'all see a GCF?
Yeah.
What is it?
1/3.
-1/3. And if we factor out the -1/3, do you see that gives us -4x minus 5? All right, so this one obviously has a vertical compression and a reflection. So this one's going to open how? Down.
Or did you
Alright.
have to do the negative, or could you just like not
Yes.
the negative?
Yes,
You have to.
you have to on these. All right, how does this trinomial factor?
You're still good on.
X minus 5, X
Hang in
plus 1.
X plus 1. Okay, so now it's in completely factored form. I've got all the information I need to be able to correctly graph this. Uh-oh. A little graph crazy right there. And I'm just going to shift this. Okay, here we go. So I need a 0. Where would my zeros be? Let me turn this into 0. So what would my zeros be?
Positive 5.
5 and -1. Now, this -1/3, that didn't change my zeros at all, did it? What does that -1/3 represent?
The
Vertical
compression.
Good. All right, so I need a 5. I need a -1. Where's the axis of symmetry going to be?
3.
It's going to be above
Positive 2.
the x-axis.
Okay, so we add these together
No, my bad. Like,
and divide by 2, so it's going to be x equals 2.
Vertex is going to be above.
So we know it's right here, right down the middle. Okay. Now, there's a couple ways I could do this. I could plug in this 2, or I could think about what effect did this have. This is over 3, isn't it?
Yes.
Okay, so normally when I go over 3, I would square it and get 9. But I have what right out here? A -1/3. So I went over 3 and down 3. So I do the reverse of that. Up 3 and left 3. There's my vertex.
Wow. Wow.
Gotcha.
So my vertex is the point 2, 3. Now if I took the 2 and plugged it into here, guess what I'd get out? 3. But it would get ugly before I got there, wouldn't it? Does it make sense thinking about our moves? Okay. So this is a nice little vertical compression. And on this type of graphing, if you're graphing using factored form, I'm okay with seeing your x-intercepts and the vertex. So as before, I required 5 points if they'd fit. Here, I'll just take 3. Okay? Now, I want you to try these 2, but instead of having to graph them, just find the zeros for me, and we'll talk about what would the graph look like. So you try 5 and 6 here.
Okay.
Okay. Let's take a look. Did you get x equals 6 or negative 1?
Why can't it be
Why-
bigger for that?
Yeah, why is it 4?
I got that, but
Like if you put a point at each of them, why do you put 4?
There will be a point at either one of them. Either using 6 or negative 1 makes this have a product of 0.
Oh, alright.
So, the zeros of the function are 6 and negative 1.
Oh, okay.
The zeros of this function are 0 and 8. Is that better?
Yeah.
Okay. All right. Let's say I had given you factored form. What if I did some of the work for you? So this is extra right here because I've already numbered everything. Let's say I gave you h of x equals 2x plus 5 and 3x minus 2. What are the zeros?
negative 3 and
They aren't integers, are they?
No.
No.
So you
No.
could do.
But to find the zeros, don't we just take, really what we're doing in our head is going, okay, this is going to equal 0, or this is going to equal 0, right? Isn't that kind of what we're doing in our head? And so to solve this, you would move that over, and you would divide by the 2, and you'd get negative 5 halves, or you'd move this over, and divide by 3, 2/3, right? Now, anytime our factor is in this form, ax plus b form, and we want to know where it equals 0, we do something every time in our head that we don't realize we're doing. Every time we move the constant over, don't we? And then every time we're dividing by the coefficient. So when it's in this form, you can go straight to the answer because you know every time you do the opposite of the constant divided by the coefficient. Negative 5 halves. Isn't that what I got?
Yes.
Positive 2/3. Isn't that what I got?
Yes.
So you guys ought to be able to do this thought process in your head. The opposite of the constant dividing by the coefficient. Okay, so we were looking at zeros because we were speaking in terms of functions. Well, what if instead of a function we just had an equation? Could we use the same idea to solve an equation?
Yeah.
Yeah. To find the roots of an equation, we can use the same idea, but the first thing we have to do is set it equal to 0. And to set it equal to 0, we just have to move that 1 over. Does that quadratic equation factor? Yes, this is a difference of squares, isn't it? 3x plus 1 and 3x minus 1. So x will be the opposite of this divided by that, negative 1/3, or the opposite of this divided by that, positive 1/3. Now last year we didn't solve it that way. You didn't know how to factor until last week. Well, some of you did. Others of you did. How did we solve it last year?
We did it. I mean,
Yeah, we did. Because I just did some in
Into
ACAC.
the calculator.
Oh my god.
We divide by 9,
Awful.
then you square it.
and then we take the square root, wouldn't we?
Yes.
So when we take the square root, you always get plus or minus.
Yes.
Yeah.
So you get plus or minus 1/3.
Oh my god.
So I really think this one is the easier way to do this problem. And so if I was, deciding how to do it, I would solve this one this way. But will that way work for this one?
No.
No.
Good, because I don't think that one.
No.
Okay. So
Wait. You divide by x.
factoring worked for this one. Factoring will work for this one.
Yes, it will.
Now factoring won't always work because not everything factors. But this one does. So first thing I'd want to do is set it equal to 0 by moving that 40x over. And since I'm moving it over, I'm going to go ahead and put it in the right spot. Okay, what do we do, folks, to factor?
Take out 2.
Take out 2. Good. Now what do we do?
You can do the trial and error.
Perfect square trinomial. Good.
Yeah.
It's a perfect square trinomial. So this factors to 2x, and this is 5, and we take the sign of the middle. If I double that product, do I get negative 20?
Yes.
Yes. So it's properly factored. Now, in terms of solving an equation, which is different than a function, does this 2 matter for an equation? Think about that while I show you this. Is it fair to use the division property of equality and divide both sides by 2?
No. Yeah.
Yeah. So that 2 went away. And over here I got 0 divided by 2. And 0 divided by any number is still 0, isn't it?
Yeah.
So, did that 2 matter? No. Now, if it had said 2x out here, would it have mattered? Yes. But because it was just the constant 2, and it's an equation, not a function, it's not going to change my outcome. So, now I know that this is 2x minus 5 times 2x minus 5. And so I know that x is going to be the opposite of this, positive 5, divided by the 2. And you'll see later on, when we combine this with graphing, that this is considered a double root. Why do you think we call it a double root?
Because it's 2. Because it's 2 and
Yeah. And if we graphed it, you would notice that 0, if this were a function and we graphed it, that 0 is actually the vertex. The 0 is the vertex. If we thought of this as y equals 2x minus 5 squared. So whether we come out from the left or the right, we're right there. And we have 1 0, and we call it a double. This is a double root for this equation, and it ends up being the 1 0, which is the vertex. Okay. One last thing we're going to go over before you have the rest of class to work, and it's an application. How would we apply some of these things that we've been looking at? And I have talked about these quadratic equations dealing with gravity before, but your book does a great job explaining what everything means. It says, any object that is thrown or launched into the air, such as a baseball, basketball, soccer ball, cannon, any projectile that is launched, will follow this formula. The general function approximates the height of the object, so how high off the ground is the object, compared to Earth after t seconds. How high above Earth is the object after t seconds? So that it's the height of the object, not the distance it's traveled. That's a different formula. It's the height of the object. So, did you guys know that gravity affects objects 32 meters per second per second?
it does.
Yeah.
Okay, 32 meters per second per second. So this formula is -1/2 times the effect of gravity times time squared. Well, what is -1/2 times 32?
-6.
Oh, that's not meters, that's feet. I'm sorry. In terms of meters, what would the number be? 9.8 meters per second per second.
Thanks,
Okay,
It's you.
good. In science, you will do meters per second per second. And do you guys write it as meters per second squared?
Yes.
Yeah.
But you say it meters per second per second? Okay, good. So this one's in terms of feet, so we're going with 32 feet per second. And you're writing it like this, so I'll stick with the same form. And so when we plug it in here and we take half of it, this number ends up being -16. Well, in your science book, you probably see a lot of -4.9s. Because what is half of 9.8? 4.9. Okay. Now, this V0, that's the initial velocity at which the object is moving. Its initial velocity. And the H0 is the initial height. And with both of our problems, we're kicking a ball that's on the ground. So what would h naught be if it's on the ground? How far above the ground is on the ground? 0. But we could launch something from a different height, and we will be doing that soon. Ooh, let's actually launch something.
Yeah.
Yes.
Rockets.
Watermelon.
That'd be fun. Maybe we will.
Oh yes.
Watermelon.
Like AlphaSoft the rockets.
So let's take a look at this one. It says a soccer ball is kicked from ground level, so we know h naught is 0 feet. With an initial velocity of 32 feet per second, so v naught is 32 feet per second. After how many seconds will it hit the ground? So what is the height where it hits the ground? 0. So what are we looking for on this function? The zeros. So let's go ahead and write our equation. The height with respect to time is negative 16t squared, because that's the effect of gravity, plus the initial velocity, which in our case is 32t, plus the initial height of the object, 0. Do I need that plus 0 really? No. Okay, now because we want to know when the ball hits the ground, we want to know the zeros of the function. Can we solve this by factoring? Yeah, what's the GCF?
16.
Negative 16t. And when we factor that out, what are we left with?
T minus 2.
Okay, so what are my zeros?
2.
0 and 2. So that means the object had a height of 0 at 0 and at 2. And what is my vertical stretch compression?
Negative 16.
Negative 16, which means it's opening down. And my first move would be over 116. We'll just say this point is at 116. And so it would look like this. All right? Now, that is not distance. This is time in seconds. This is the height of the ball with respect to time. So this is not the path the ball took, is it? No, it's just the height of the ball with respect to time. So that means it was kicked at time 0 and it landed 2 seconds later, and its path reached a maximum height of 16 feet. Yes, Sid?
If you wanted to use distance, wouldn't you have to have a z coordinate?
If we were using distance for us, we will have a separate function that we can plug into. And it will be distance with respect to time, which will be a second function. And then once we find our time, we could plug in how much distance do we travel in 2 seconds, and that would give us the total distance that the ball traveled.
Wouldn't you just have double? With the height?
No. This is the height. It's different.
Okay.
Yeah. So I would have to give you a second function to represent distance. So we might say it traveled a distance of 12 feet per second. So we would plug in 2, and we would get that the ball went 24 feet. Okay? So you would just have to have a second function. All right, you try. Number 10. when we plugged into this function, we still have the negative 16t squared, but this time we've changed our initial velocity to 48, and we're still kicking from a height of 0. So we can just kind of ignore that part, factor out the GCF. We get that the times that the function has a value of 0, that means when it was on the ground. We're at 0 seconds, that's right when we kicked it, and again at 3 seconds. So how long was the ball in the air? 3 seconds. That's how long it took it to hit the ground again. Yes, sir?
It's about finding how high it went. Wouldn't you just do the negative b over 2a?
Sure. To find the height of the ball, you could do negative b over 2a, but that just gives you the x. And we know that the x is halfway in between those two, so we know that x is 1.5. So to find the height, you would have to plug the 1.5 back into your function.
Okay.
So you'd have to plug in 1.5 there and 1.5 there. Okay, so your homework is out of your workbook. It's page 357, 1 through 6. So you're going to finish that up on page 358. And then page 359, 3 through 10. You have the remainder of class to work on your assignment. You're welcome.